Hi everyone, I'm Nikhil Manjunath.
I'm Krishna, Dheeraj, Krovi.
Today we'll be presenting our final project for EE538 titled Trojan map. A brief overview of our project. We're building a map of all the locations around USC campus using C++ data structures and graph algorithms. As you can see from the picture, the red dots on the graph represent the various locations around USC, and the green lines suggest the paths connecting the locations. The main objectives of the project is to implement the following algorithms: autocomplete, find location, calculate shortest path, traveling salesman problem, cycle detection, topological sort, and finding the k closest points. The first algorithm implemented is the autocomplete function, where the user inputs an incomplete string and the autocomplete function automatically displays all the locations on the Trojan map which start with the input string. For example, if the user inputs CH, it displays all the locations near USC that start with CH. The time complexity for autocomplete is O of n. Here are a few other outputs of autocomplete function. If there's no location found, it's displayed as no match location, and if there's an invalid string that is being input, again we're finding no match location. The next algorithm implemented is the find location coordinates. In this algorithm, we search for the location on the Trojan map, and if the location is found, we're returning the latitude and longitude corresponding to the location. The algorithm also plots the location on the Trojan map. For example, in our input, we're giving as ralphs, and the algorithm finds ralphs on the Trojan map and outputs the latitude and the longitude. The time complexity for find location is O of n. We've added an extra feature for the find location called the find closest name. This works on the edit distance algorithm, where if the location is incorrectly spelled, the edit distance algorithm goes through each node in the Trojan map and finds the location which has the closest resemblance to the incorrectly spelled string. For example, if Ralph is misspelled, the algorithm automatically finds the correct location. So here we can see how the edit distance works. For an input of Cove, we get Kava as the corrected word. From the table, you can see that we're comparing each character of both the strings, where first we're comparing C with a C, and since both are matching, there's no distance. But whereas when we compare CO with C, we can see that the distance is 1 because by adding an extra character to C, we get both the strings as same. And so finally, when we compare both Cove and Kava, we can see the distance is equal to 2 because if we replace O and E with A's, we get the same string. The next algorithm implemented is the shortest path, and as the name suggests, we're finding the shortest distance between two locations. Here we've built the Dijkstra as well as the Bellman-Ford algorithms. The Dijkstra algorithm is a greedy algorithm which searches for the nodes with the lowest overall cost, and this algorithm generates the shortest path on the fly. The time complexity for Dijkstra is O of E into log D, whereas the Bellman-Ford algorithm is an algorithm which goes through all the neighbors repeatedly, and then once it's completed going to the neighbors, it computes the minimum distance for each path. The time complexity for Bellman-Ford is O of BQ, but this can be made faster by implementing the early stopping algorithm, which reduces the time complexity to O of E into V. Here we're comparing the time taken by the Dijkstra and the Bellman-Ford algorithms in our Trojan map for different sources and destinations. We can see that Dijkstra takes less than a second to compute the shortest path, whereas the Bellman-Ford takes a slightly longer time of around 5 to 6 seconds. As I mentioned earlier, Bellman-Ford algorithm can be made faster by implementing the early stopping algorithm. In this algorithm, we keep a track of the number of relaxations, and when there's no change in the relaxation between two computations, we stop the Bellman-Ford algorithm, thus saving computational time. So here we compare the Google Maps output with the Trojan map output for the shortest distance. We can see that both the maps are outputting the same shortest path, and the distance output is also 0.9 miles.
The next function which we implemented is traveling Trojan. This is similar to the famous traveling salesperson problem, where we have few locations to travel. So first, our algorithm works in such a way that we give the input as the number of locations, and the function randomly picks n locations on the Trojan map, and it runs algorithms to find the shortest path and returns the path as an animation using OpenCV. The algorithms which we implemented are brute force, backtracking, and 2-opt. Brute force considers all combinations of locations and computes the smallest distance. The backtracking minimizes some of these using dynamic programming and it reduces the number of computations. And the 2-opt is a local optimum finding algorithm, which uses a concept called swapping mechanism, where it considers all possible combinations of nodes and computes the distances by swapping these nodes and maintains the minimum path traversed. The time complexities involved in brute force and backtracking are similar to O of n factorial, and the 2-opt is faster and its time complexity is O of n squared. Here we can see the traveling Trojan outputs for 4 nodes. The brute force computes it pretty quickly. The backtracking takes some iterations, but it almost is similar to the time taken by the brute force, whereas 2-opt is much faster. In the next slide, we'll see the computational results too. Here we can see the time taken by each of these functions. So here we can see that 2-opt is the fastest executing algorithm. Cycle detection. In cycle detection, we give a region of interest, and if there are closed paths in that, it returns true. But a cycle means that when we start with a node and end at the same node without traversing the intermediate nodes more than once, a cycle is complete. So the algorithm which we implemented uses DFS and dynamic programming. The time complexity involved is O of n plus E. Here are the results of the cycle detection function. Here we gave 2 examples, one which gave us a result of a cycle detected and one without, and these are plotted on the Trojan map too. Delivering Trojan. In delivering Trojan, we have 2 main concepts. One is the locations to travel, and one is the dependencies. The dependencies are basically the criterion on which the traversal should be made on these locations. So this dependencies file contains criterions on locations such as, in our example, we have to go from Raz to Chick-fil-A. Our dependencies would be that Raz should be visited before KFC, and KFC should be visited before Chick-fil-A. So the algorithm which we use to implement this delivering Trojan is DFS, and the time complexity involved is O of n plus E. Find nearby. Find nearby is similar to Google's Find Nearby feature, where we type in such as a cuisine name or a restaurant of our interest, and we get the nearby locations. In our function, we give the attribute name, the location of where we are, the search radius of how far we'd like the places to be shown to us, and the desired number of locations. For implementing this, we used max heap or priority queue to find the k closest locations. We also display these k closest locations on the Trojan map. The time complexity involved in this function is O of n squared. This is the output for Find Nearby function, where we search for bars near Raz. We wanted the places near Raz for a radius of 10 miles, and we would like the maximum number of results to be 10, but the max we got here is 3. Conclusion. In conclusion, we'd like to say that we implemented this project with some of the most important data structures and algorithms, and we saw how optimizing algorithms could reduce the time complexities. The project was really exciting because we got to know the intuition of how Google Maps, Apple Maps work.
For future scope, we think that the project can be extended to add bookmarks for frequently traveled places so that it can be accessed quickly. We can also improve the algorithms to have faster execution time and also extend support for different modes of transport like bike and automobile. Thank you.
Thank you.